Good afternoon, everybody. Welcome to lecture. So the big news is that exam one has been graded, recorded, and keys are posted, so you can look there and see, depending on what version of the key you've got, just get the right, or version of the exam you have, just pick up the right key. But the scores were pretty good. The average was 75.7%, which is consistent with good scores throughout the recent years in this class. It's better than last year by quite a bit, actually. So overall, I thought the class did really well. There's a lot of people in this range right here, which you're getting it really well. A lot of people in this range, which are getting it, but room for improvement. And then, struggling over here. So if you're in the lower half of the graph, you really want to get yourself above, like like 65 or better would be good. So if you're not quite there, come see me and we can talk about what you can do to help improve your scores. Let me know after you have a chance to look at your exam and look at the key if there's any that you're not sure of, why they exactly are the way they are, and we can talk about it. And remember that you get to drop your lowest exam. So there's going to be 4 exams total this semester, 3 more on the way. They're all worth the same amount, and at the end I'll drop your lowest one, and the best 3 of those 4 will count towards 3/4 of your grade in the course. So if this exam was not good, doesn't mean you're going to have, a poor chance of succeeding in the course. Not at all. So you can still do better. You just have to maybe adjust your trajectory. If you're doing great, if you're up here, fantastic. Keep doing what you're doing. And we're going to be moving into this stuff that's not spectroscopy now. So we did a lot of spectroscopy on the first exam. And so if spectroscopy isn't really your thing, maybe the other exams will be, easier or better or whatever. But anyway, come see me if you have any concerns. So now I want to talk about the survey question that we had, which was about unique isomers that you would get if you did a monochlorination reaction with this alkane by putting in chlorine gas and giving it some light energy. So this is a radical reaction. We talked about these kinds of reactions last time. We're going to talk about the mechanism of these kinds of reactions today. But essentially, it's a radical process, and you have to think about what are all the possible products I could get out, including stereoisomers, if I were to replace every one of the H's on this molecule. And there's a lot of H's in this molecule, but they're not all going to give unique products. So the challenge is try to figure out which ones would give you unique products and what are all the possible products you could get. And the scores, let me submit this. Actually, let's take a look at the key, because the key or the answer to this one is good. It's got a lot of detail in it. Correct answer is 4, because I'll move this mouse off of here a little bit. So if you replace one of the H's on the end methyl groups, you make an H dot there that can pick up a Cl dot, and there's no new stereogenic center that forms at that carbon, but the adjacent carbon becomes a stereogenic center, and that's what gives 2 possible outcomes, this molecule and that molecule. So substituting at one of the methyl groups gives 2 possible chlorination products. If you substitute at this, what's called methine position here, the CH, you generate a dot there, put a chlorine in its place, you get this one, but there's no new stereogenic center in that molecule, so there's just one possibility. Then the other possibility is if you substitute in the middle, which is take off one of the H's here and put a Cl there, you get a molecule that, again, doesn't have a new stereogenic center, so there aren't stereoisomers to worry about. So 1, 2, 3, 4. 4 is the number. The class on this one, I know the statistics were kind of mixed. The correct answer 4 was the most popular answer, but a lot of people selected 5 as well. So if you selected 5, think about the 5 that you thought were there, and then think about what, if there are any 2 of those are the same. That's probably the issue that you had. So do you have any questions about this? Okay. The next thing I wanted to do was to just talk a little bit about AI and how can it be useful for studying for this course. It is all over the place. I mean, AI is hard to avoid. It's kind of trying to creep its way into all aspects of like daily life in our economy. And so a question you might have is, how useful is it for organic chemistry? And I've been using it a lot and trying to just test it out to see what it can do and what it can't do. And there are times when I've been really impressed by its abilities to come up with really good solutions to complicated chemistry problems. But then other times it doesn't get it right. Makes a lot of mistakes, and that's a problem with AI in general. Is that it is really useful. It throws a lot of good answers, but every so often it just gives you something that's just not right. Sometimes they're really off the wall kinds of things, and you can tell. But sometimes it's a solution that seems like it could be right, but there's something wrong with it. And so I just want to share with you like an interaction that I had with AI. I spent lunchtime talking with ChatGPT about this survey question, actually. I'm just like, well, let's see what it can do with a survey question like this. So I'll show you what came up when I went through this. All right, here's my session with ChatGPT. So this is just a screenshot of the question, and it's exactly what you see in Canvas. And I asked it, this is my prompt. I said, try and answer this question. And it says, oh, great, let's count. The substrate is 3-methylpentane. Well, it's not 3-methylpentane. It's 2,4-dimethylpentane. And that's a really big mistake because if you don't start with the right molecule, you can't end with the right question. So it gave it gave a technical sounding explanation that probably, I haven't even checked, it might be right for 2-methylpentane, but it's not the right substrate. So, it's a big, long explanation. Then what did I tell it? I said, scroll this up here. Look again, the starting material is 2,4-dimethylpentane. And I thought for 30 seconds, and it said, you're right, 2,4-dimethylpentane. And then it showed me a condensed structural formula, and it said it has C2 symmetry through C3, and that's right on. So that's good. It's recognizing that. And then it went on to talk about all the different positions. And here's a problem, a big problem, is this is wrong. So it says methine H at C2C4. So it's talking about that one. It says when you make do a chlorine substitution there, you get a new stereogenic center, but that's actually wrong. So it didn't recognize that, and that's going to cause it to have all sorts of problems when it tries to come up with the answer to this. And so it says unique stereoisomers 5. Well, that's not right. So I went on and said, replacement of the methane, I should have said methine here, hydrogen at C2 or C4 does not produce a new stereogenic center. And then I thought for 51 seconds, it really had to burn some electricity on this one. And it said, you're right, C2, C4, it's one of the other things about AI. I guess it uses a lot of energy. 2 identical methyl groups after substitution, so no stereogenic center is created here. And then it went on and it talked about a whole bunch of other things, and it said 6. So it's like it's getting further away. So at that point, I just took a screenshot of the solution, and I said, you are wrong again. Look at the solution in the screenshot. And then it said, you were right. Thanks for pointing me back to the screenshot. And then it went on to have a reasonable discussion of the answer. And then it asked, and a lot of times it follows up with something. The ChatGPT is just never done with the conversation. It's always like, well, what about this? Do you want to do this? Do you want to do that? And it asked me, do you want me to make a diagram of this? And I said, sure, go ahead and try. And it came up with this, which isn't terrible. I mean, it's got the basic connectivities. It doesn't look like any kind of structure you or I would ever draw. But the problem is that the labels aren't really in the right spots. I can see it's kind of a rough skeletal structure of the molecule, but it's not really good enough to be useful. So I asked it, what did I ask it here? I asked it, can you draw this as a good-looking Lewis structure? And actually, no, in fairness, this is pretty good. This is decent. It's got A and D and D. And what it's trying to say is that if you remove like A and D, although they're identical methyl groups, replacing a Cl there would give you a different molecule because you get stereogenic centers. So this is actually pretty good. I've had other issues where I've asked it questions about like alpha cleavage, for example. I asked about alpha cleavage of acetone, and it gave me an answer in text that was spot on. I mean, it was textbook. It was really good. Then it asked, do you want me to draw you structures of this? And I said, yes. And what I got out was something that didn't even have the right atoms in it. It was just so far off, I couldn't really believe it came up with that. So the answer is, should I use ChatGPT to study with? I don't know. It maybe if you're out of ideas and you want some inspiration, give it a try, but just recognize that it gets a lot of things wrong. And so if you don't have the ability to pick up wrong answers, you might get led down the wrong path by it, and that's what I worry about. So, but definitely tinker around with AI. If you think it might help, give it a try, because it's technology that's definitely gonna have a huge impact on the world, and eventually it'll get really good at chemistry, I'm sure. Organic chemistry, it'll probably replace me someday, but for right now, it's not quite ready for that. So, so anyway, potentially useful tool. Great for lots of things. Like if you want to do air frying of like chicken nuggets or something, and you got like a recipe that just says the oven and the microwave, spot on every time from what I've seen. So, and for some chemistry stuff, great, but kind of tricky sometimes. So all right, so that's my little discussion. So, all right. Oh yeah, this is the problem with this one. Yeah, this might not be all that useful. Okay, I'm going to stop projecting. It is kind of fun to talk to, though. I mean, it can have a sense of humor if you ask it to. I find it amusing. Sometimes it can be kind of funny, actually. So, and there are actually some. One of the things I asked it was, what should I tell my students about how to use you for studying? So this was one of the questions I had for it, and it gave actually a pretty thoughtful response, and I'll post that in the discussion. But essentially, what it said was something to the effect of, treat me like you would a study partner, a student study partner. I'm there to bounce ideas off of, but I can make mistakes, and yeah. But it can also condense or complicated data into an easy to understand kind of nugget. It can, basically, it can sometimes really help. So it's just hard to say, is it good or not? Okay, so we are talking about halogenation, mechanism of halogenation. So let's do first of all, the overall mechanism here. So this is CH3 reacting with Cl2 with either heat or light energy to give CH3, CH2, Cl, and HCl. And what we're going to do is look at the mechanism of this reaction and study it step by step to try to understand what happens at every stage of the process. So the first reaction that happens in all these radical reactions is an initiation reaction. We talked about this last time, but this is review because definitely you don't want to miss this. So if you put in light energy or heat energy, you break the Cl-Cl bond homolytically. You break it like that, and you get 2 Cl dots. And now you have radicals, and these things can go on and do additional reactions. And so this is the initiation reaction. And then there are propagation reactions. I'm going to call this one propagation reaction number 1, because there are going to be 2 propagation reactions that we're going to need to think about in order to get through the mechanism. The first propagation reaction relies on the product of the first reaction, the initial initiation reaction. It's a Cl dot that's going to be a reactant here. And then this Cl dot is going to react with an ethane molecule. So I'm going to draw a molecule of ethane. I'll do CH3 on the left, and then on the right side, I'm going to draw out the H's. And what happens is the Cl dot goes and grabs an H dot out of the ethane, and there are 6 identical H's, so it doesn't matter which one it grabs. I'm going to pick on this one right up here. I'm going to show this reaction by taking the dot on the Cl, drawing a half-headed arrow somewhere. It just has to, anywhere in space is fine. And then I'm going to take one of the electrons out of the CH bond and pair it up by having those 2 arrows meet. And with that, 2 fishhook arrows meeting in space is saying we're going to make a new bond between the Cl and that H. And then the other H in this bond has to go to that carbon. So we're getting 2 products out of this reaction. There's an HCl that comes out of it. And then the other product is this CH3 CH2 with a dot. So there's a new radical that formed here. This is characteristic of a propagation reaction where you start with a radical and you end up with a different radical, a new radical. So we had a radical on the left side, a Cl dot. Now we got a carbon dot. So we made a new radical, but we haven't created or destroyed radicals. But this produces one of the 2 products. If you look at this, there's HCl right there. So we've gotten kind of almost halfway there. So then there's propagation reaction number 2. That happens next. Propagation reaction number 2. This is going to use the product from the previous reaction, which is the ethane radical. So I'll redraw that here. CH3, CH2 dot. And this is going to react with another molecule of chlorine. So first thing is that I should tell you about this is I got to say there's still chlorine around. So if you look back to the previous board here where we talked about the initiation reaction, Cl going to Cl dot, this reaction doesn't go to completion. It's not like all the chlorine goes to give dots. You just get a few dots, basically. It goes a little bit. That's important because when you do one of these radical reactions, you have a small number of radicals in solution that are going around, but they don't. But you're not going to completely consume the chlorine. You're just going to generate a few Cl dots, and then they do reactions. But the this carbon dot that we made over here, that can still find a chlorine molecule to react with. So they're still around. So chlorine, ClCl, this carbon dot is going to steal a Cl dot out of this molecule. And the way that will work is I'll do the same thing here where I did before, where I take 2 fishhook arrows, the dot on that carbon. I'm going to pair it up with the electron on this chlorine that it gets from breaking this bond homolytically. The other electron goes on that chlorine there. And then the 2 products that come out of this are CH3, CH2, with a chlorine here, and you get a new Cl dot. And the thing about this Cl dot is this is the reactant that you need for the first propagation reaction. So let's go take a look at that first propagation reaction again and just have a look at it. So Cl dot reacts with ethane to give carbon dot, and then carbon dot reacts with chlorine to give Cl dot. So these propagation reactions occur over and over again. The product of one is the reactant in another, and this is what's called a chain reaction, when reactions happen after each other, almost like a dominoes falling. One reaction leads to another. So the propagation reactions occur over and over and over again, and this is how product accumulates. You get HCl from the first propagation reaction, and then you get this chloroethane molecule from the second propagation reaction. And those are the primary ways that the product gets generated. There are other kinds of reactions, though. The other way that you can get product is there's a set of reactions called termination reactions. So termination reactions are when two radicals get together, and then that tends to slow the reaction down. So there's different types of termination reactions. If you consider what are all the possible radicals that are in solution, and then what would happen if they got together and reacted, one possibility is that two Cl dots got together, and if they did, that would be a termination reaction that gives Cl-Cl. That would tend to destroy radicals. You have 2 here in the starting materials and 0 in the products. So this slows down the reaction, makes it go slower. The other possibility is that, or one other possibility, is that you might get the carbon radical reacting with the Cl dot radical. And if those two got together, they would generate the product. So the product can also form, the carbon product can also form from a termination reaction. The thing to remember, though, is that these radicals are really low in concentration, so they don't find each other in solution very often. So although this reaction produces product, it doesn't produce a lot of it. So mostly it's the propagation reactions that are producing product. You get a little bit, but it's not mostly from this reaction. It's mostly from the propagation reactions. And then finally, the other termination reaction that you could get would be if 2 of these carbon radicals were to find each other in solution. One of these and one of those got together and made a bond, you would end up with, there's a skeletal structure of it, that'd be butane. You put 2 ethyl pieces together, you make a new bond between the 2 CH2s, and that's butane. So you get a little bit of this. I'm going to say small amount. And just for reference, I'm going to do the same thing over here. I'm going to say small amount. So the termination reactions really produce small amounts of products. They don't generate lots. You get enough of this that you might be able to detect it, for example. And I think there's a homework question that asks you something about that. Predict a product that would come out of this, and then you have to know about the termination reaction having the 2 organic pieces coming together. So that's a reaction that happens sometimes. This collection of reactions, the initiation reaction, the 2 propagation reactions, and then the termination reactions are all the things that go on that help explain how the products get produced from the reactants that you start with. And just as a reminder, those reactants were ethane, Cl2, some activation energy in the form of heat or light, and then you get chloroethane and HCl. And you could draw the same mechanism for pretty much any alkane. Ethane isn't special, it's just simple because it's only got one type of proton. But do you have any questions about this, like how that mechanism works? Okay. Well, let's talk about then a little bit more about chlorination of alkanes, but chlorination of alkanes that are just a little bit more complicated. So that survey question that we looked at, you could see that you get lots of potential products if your alkane is even just a little bit more complicated than like ethane, for example. So we're going to try to understand if any of those, if there's any preference for one of those versus another. In other words, is it a totally random mixture, or do you sometimes get a preference for one versus another? So this section is about chlorination of other alkanes. And I'm going to make the alkane just a little bit more complicated. I'm going to put one more carbon in it. So our mechanism, we looked at ethane. I'm going to look at propane. So propane is a 3-carbon alkane. And it has 2 types of protons in it. There's a mirror plane of symmetry that runs through the molecule right here. And the 2 methyl groups are the same as each other because they're reflections in that mirror plane. The 2 CH2s are the same as each other because there's another mirror plane that runs through the molecule this way. So you've got 2 types of H's, and if you replace an H on a methyl group, you get one type of product. If you replace an H on the middle carbon with the chlorine, you get a different product. So here are the 2 products. The 2 possible products. You could get CH3, CH2, CH2, Cl, where the end carbon got the chlorine. That's one possibility. The other possibility is you could get the product where the chlorine goes in the middle. On a secondary position. And let's just think about, like, statistically what the odds of that are. So what do you think about, like, just if it were totally random, how many times would it go in a methyl position versus a CH2 position? 3 to 1. I hear some people kind of saying 3 to 1, and that's right. There's 6 of this type of proton, and there's 2 of that type of proton. And what happens is the Cl dot just bumps into an H, and it pulls off an H dot. And since there's a lot more methyl protons, the likelihood that it's going to bump into one of those is just a lot higher. There's 6 of those and only 2 of these. So the expected ratio based on statistics would be 3 to 1, or 6 to 2 if you prefer. 6 to 2, it's 6 protons of this type, 2 protons of that type. But I'll simplify 6 to 2 down to 3 to 1, and that's what you would get if there was no difference in reactivity between methyls and CH2s. You can do the reaction and you can study the product ratio, and it's not a 3 to 1 ratio, it is actually a 1 to 1 ratio. So even though the CH2 positions there's less of them, they seem to react more frequently than the terminal positions. And so what you can deduce from this is that these H's are more reactive than the methyl H's. And the whole reason is that there's the substitution difference. So the H's on the ends, these are primary H's. They generate a primary radical, which is higher in energy. It's harder to produce. It forms more slowly. Whereas if you put a dot on a carbon that's a secondary carbon, it produces a more stable radical. So it's more stable, it's better there, forms more easily, faster. So that's why there's this slight preference for the more substituted chlorine, carbon getting the chlorine. So here's the conclusion. There is a slight preference for chlorination at the more substituted carbon in this case. And that is just the way chlorination works. isn't really a strong enough selectivity to be particularly useful because you still get out a fairly complicated mixture. 1-to-1 versus 3-to-1, it's still not a lot better. In some ways it's worse. If this is the one you wanted and you got this, that'd be headed in the wrong direction. But that's the way the chlorination works. Now we're going to talk about bromination, which is a very similar mechanism, but Br dot and Cl dot behave differently because the size of the atom is different. So Cl dot is a dot on a small atom. Br dot is a dot on a much larger atom. And if you remember anything about periodic trends with basicity, the larger the atom, the more stable the anion. It kind of works the same way with radicals. Br dot is a bigger atom. Chlorine is smaller. So Br dot is Br dot is more stable than Cl dot. So we're going to see how that works. Bromination. So when people did the same reaction with propane and they substituted chlorine for chlorine, they substituted in bromine, the same possible products come out. CH3, CH2, and instead of chlorine, you put bromine in there, and you put in light energy or heat energy. The two possible products, again, are putting the halogen at the end of the chain, or putting the halogen in the middle of the chain on the secondary position. This is product number 2. And again, there's an expected ratio based on statistics. It's what you would expect to get if all the positions, all the H's were equally reactive. So 3 to 1. It turns out, though, that when you do this reaction, you get 1 to 99. Wow. So that's different. It's really different. There is a strong selectivity for bromination at the more substituted carbon. So here is the bottom line. Bromination strongly favors reaction at the most substituted carbon. To the point where this is a really minor product, the primary bromide. And there'll be questions in the homework that'll ask you about what's the major product of this bromination reaction. And the thing you have to remember is that bromination really is highly selective for the most substituted position. So find the most substituted position that has an H on it, pluck the H off and put a Br in its place. And you got it. Now, a few notes about that. Let's go through a couple of examples just to clarify a few things. It's pretty much that simple, but there's some situations that I want to just call your attention to. You can still get stereoisomers, and that you have to account for very often. So for example, trying to think of how I can. All right, I'll do this. I'll do this one. So we've got an alkane here that's got a lot of different kinds of CHs, but there's one spot where there's a tertiary H right there. If you took inventory of all the kinds of H's, hydrogens that you have, you got primary hydrogens here, 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 and here. You got secondary H's here, here, and there. And then you got one spot that's got a tertiary H. That's going to be the hot spot. That's where when you put bromine in and either light or heat, it's going to pick on that H because that's the most stable place to put a dot. And Br dot is a pretty stable radical, and it takes its time. It doesn't just grab off any old H dot. It picks the best one. So it will grab that one, and you get this intermediate where there's a dot here, and then that carbon dot grabs a Br dot off of a molecule of Br. So bottom line is there's a Br that ends up in that spot. And that produces this product, but there's a new stereogenic center there, so you have to make sure that you're aware of that and just draw the two possible stereoisomers that could result. So one possible form is with the methyl on a wedge bond and the Br on a dash. And then the other possibility is the opposite of that, the one that has the opposite stereochemistry with Br on the wedge and a methyl group on the dash. So those are the two major products that come out of this reaction. If you've got a molecule that has two tertiary positions, you could get substitution to either one of them. So it's a possibility to get two major products if they're both equally substituted. So that's another thing you might see. All right. So the next section talks about halogenation as a tool in chemical synthesis. So what that is like, how can you make these reactions useful for producing a product? Chlorination can be useful, but it's really messy. It produces lots and lots of isomers, constitutional isomers and stereoisomers. So I'll just title this section here, halogenation as a tool in synthesis. As a tool. Chlorination can be useful if the product can be produced without a complicated mixture. So in some cases, if you've got an alkane that's complicated and has lots of different types of H's, chlorination probably won't work very well for you. It's not going to give one product selectively. It's going to give you every possible chlorination product. And some of them there'll be a little more of, and some of them there'll be a little less of, but it's still going to be a complicated mixture. But here's an example where it might actually be useful to chlorinate a molecule. So cyclohexane, for example, has 12 hydrogens, but they're all identical. And it doesn't matter which H the Cl dot plucks off, it leads to the same monochlorination product. So here's one where you could make this reaction go pretty well. That's the only monochlorination product you can get. Now, you might get dichlorination products if you're not careful, but you could do this by using an excess of the alkane, a controlled amount of the chlorine, like have this be your limiting reagent, not this. And then and just don't run the reaction for really long. But this is one, since there's only one type of H, there's only one type of chlorination product you could get out. Then, as we saw, bromination is useful for making highly substituted alkyl bromides. It's really good at that. So if you have an alkyl bromide, like say for example, if you, I'll take care of this one over here on the board over here. Let's take that alkane that we used in our survey question as a demonstration piece. When we did chlorination, there were 4 products, including stereoisomers. It was pretty messy, and we didn't really, we wouldn't get like very good selectivity for any of those. It'd be a mixture of all 4. But if you do bromination, since bromination is selective for the most substituted spot, we've got one spot here that's got an H. And since there's a mirror plane of symmetry in this molecule, these 2 spots are the same. So what I would predict to come out of this in really good selectivity would be that product right there. This would be a really good reaction. This would be a good application of bromination to produce one product selectively. So if you wanted this product, this would be a good way to do it. You wouldn't get a huge mixture. It'd be pretty efficient. So any questions on bromination or chlorination or how any of those processes work? Okay. There is a like kind of an enrichment section that talks about CFCs in the ozone layer. CFCs are chlorofluorocarbons, and chlorofluorocarbons have been regulated out of existence for quite some time now. So chlorines in the upper atmosphere are not as big a deal as they used to be. But basically Cl and alkyl chlorides are a problem because they generate radicals that break down ozone. So we're not going to talk about that in detail, but we're going to move on and talk about allylic bromination, which is the next topic in the chapter. So what's allylic? What does that mean anyway? We're going to start with a definition of allylic. Allylic bromination. So allylic position is a sp3 hybridized carbon that's next to a double bond of some sort. Here is an example. The carbon that is next to the double bond, this is called an allylic position. And the H's that are attached to it, this H, and this H, these are allylic hydrogens. The reason the allylic position is special is that being next to a double bond means that if you make a radical here, like you put a dot on this carbon, imagine taking an H off here, leaving a carbon dot in its place. That dot is resonance stabilized, which is the most stable kind of radical. So reactions that occur next to double bonds, they're a lot of times, that's a really common spot for reactions to happen. It's one of the really reactive places in molecules. Double bonds are reactive in themselves, but then the positions that are next to them are also reactive. So we're going to see a set of reactions called allylic bromination, where if you take an allylic molecule like this, a molecule that has an allylic position, and you put it in with a new form of bromine, and I'm going to put the structure of this material down, and we will talk about it. what comes out of this reaction selectively is an allylic bromide. So you put a bromine in the allylic position. So this is an allylic bromide. And it has the bromine in the carbon. It's basically putting the bromine in the most stable position. The idea is the same as with bromination that we looked at over on the previous board here, where it was going in the most substituted position. Let me just flash back to this for a second and talk about this. The reason that this reaction works the way that it does is the bromination puts the halogen in the most substituted position because that's where the radical is the most stable. Allylic bromination is the same way. It prefers the most stable position for the dot, and it's just that the allylic bromination, there's a double bond which can produce a resonance stabilized radical. So that's where the dot wants to go. So the mechanism is very similar. It's you form a dot at a carbon, you make a carbon dot, and then that carbon dot grabs a Br dot off of something. It just happens to be this new form of bromine that we haven't talked about yet, but we're going to get to this. But the result is you get the bromine in the spot that had the most stable carbon radical. So that's allylic bromination. Now, what's going on with this funny thing? This is called, it has an abbreviation, NBS is how you'll very often see it abbreviated. It stands for, the chemical name is N-bromosuccinimide. Succinimide is the molecule where instead of bromine, there's an H. And then N-bromosuccinimide just describes this. This is a special reagent that you use when you're doing allylic bromination. So when you see this molecule, think allylic bromination. You also have to put in some light energy or heat, but the result is you get a bromine in the allylic position. So the reason that this reagent is used is that you can't use bromine directly in an allylic bromination reaction, and I'll show you why. So people found if you wanted to do a bromination reaction in the allylic position, and say, for example, you put in bromine, Br2, and either light or heat, what you get out very quickly isn't an allylic bromide, but it's actually a dibromide. So the bromine doesn't add in the allylic position, it instead adds to the double bond. And there was, if you remember last semester, it was one of the last things we talked about in Organic 1. There's a bromonium ion that forms, a Br that's part of a triangular structure, and then a Br minus attacks it, and it opens it, and you get a dibromide. That's great if you want to make a dibromide, but if your goal is to put a Br in the allylic position right there, Br2 isn't going to do it. It reacts differently. So what people came up with is this new reagent, N-bromosuccinimide. So NBS produces the allylic bromide. So there's just different reagents to do different jobs. And that's why this N-bromosuccinimide is the one to pick to do an allylic bromination. Okay, one of the challenges with allylic bromination is just figuring out what kind of products you're going to get. So let's go through a couple of them, and then we'll go on and we'll talk about ones that are a bit more complicated. And I'll help you develop the skills that are necessary to predict all the allylic bromination products that you could get in any situation, no matter how complicated it is. And it's really not that bad. You just have to be careful that when you're thinking about your starting material, that you think of all the possible spots you could put a Br and not miss any. Here's an example of an alkene. That if we put in N-bromosuccinimide, and I'll draw the structure of the reagent up here. I think that's reminding me that it's office hours pretty soon. Thank you, computer. Okay, so light energy or heat energy. First thing is identify all the allylic positions. Don't miss any. So we have a carbon here that's got two H's on it. There's no allylic position here. We're looking for, remember, we're looking for a sp3 hybridized carbon next to the double bond. So there is there's the double bond. This carbon has an sp3 hybridized carbon here. So these are allylic H's. This one has sp3 hybridized carbon there with H's. So we have two allylic positions here. So there's an allylic position, there's an allylic position, that H, that H, that H, and that H. The thing about it, though, is these are the same because there's symmetry in the molecule. So although there are two allylic positions, they're identical. So they're going to give the same product or products. But sometimes there's more than one unique kind of allylic position, so you just have to watch for that. So the way the mechanism works is that you go through as an intermediate a radical on the carbon. A dot, Br dot, comes by and plucks an H dot off of any of these positions that are in the allylic spot, and you get an allylic radical. I will draw that allylic radical for you. And I'm going to just pick on the lower carbon of the two to put where the radical is. It'd be the same if I put it up there. Okay, and then what happens is this carbon dot grabs a Br dot off of another molecule of N-bromosuccinimide. So what you get is a bromine in this spot. Now that's a stereogenic center, and we've been worrying about those in all of our other reactions. And we could worry about stereoisomers here, but just the way that it's set up in the textbook and the way most of the time these problems work is that we're just going to ignore stereochemistry for the purposes of allylic bromination, just to keep the product mixtures manageable. Otherwise, they get to be really complicated and have a lot of products. So a lot of times what these questions will ask are, predict the constitutional isomer products. Constitutional isomer products is what this question wants. So there's one of them right there. You didn't need to put the star by it, but I just did that so you knew that's a stereogenic center. We're just not going to worry about the two possible stereoisomers. It will get produced as a mixture of enantiomers, but we're not going to worry about that. Interesting thing, though, if you looked at this reaction mixture, that's not the only thing that comes out of this. You also get this product, which looks like this. Huh. That's interesting. That doesn't look anything like what we started with over here. So what's going on? Well, the thing is resonance stabilized intermediates have more than one form of radical. So in other words, there's radical character on this carbon, true, but you have to also think about the fact that this dot is delocalized onto that carbon. So you have to draw the resonance structure. And when you do, you get this picture. So these two resonance structures are what are required to fully describe the intermediate radical. And because there's radical character here, the reaction, that carbon dot can abstract a Br dot, and that's how you get this product. So these are the two products that you get out of constitutional isomer products that you get out of allylic bromination. When we come back next time, we're going to talk about examples that are a little bit more complicated, and we're going to just go through and make sure that we can get all the products and not miss any. And then we're going to move on and we're going to talk about polymers, which seems like a really kind of like a non sequitur, but polymers, plastics, use a lot of radical chemistry, and so it'll be really interesting to see what those are like. So I will see you next week. Have a good weekend.